Right, we'll just try and race through a few of these calculations from your math paper there. So DEB 2020, question 1, it was 1E. You're looking at a titration between iodine and sodium thiosulfate, just like the bleach. Instead of doing NaClO, you're working with I2. Anyway, we'll bat around, we'll try and horse through these. The first thing it asks you for the number of moles of sodium thiosulfate. We know that. They're going to ask you that because you've got the volume and the molarity. Once you see the big M, straight away that means the number of moles per litre. How do you say in a litre? 0.1 over 1,000, and then how much have you got? 15. Now when you throw that in your calculator, 0.1, you get 0.0015, or 1.5 by 10 to the minus 3 moles per 15 centimeters cubed. Next thing you do, you could have done at the start, is the ratio. 1 is to 2 is to 2 is to 1. So we know there's 0.0015 moles of this, or sodium thiosulfate. Therefore, work out the number of moles of iodine, you divide it by 2. And is that what they asked? Hence find the number of moles per centimeter cubed. Right, we've got to be careful here. So to find the number of moles of this, you divide it by 2. Because of the ratio. 0.00075 moles per how much? 20 centimeters cubed. Your information on your iodine per 20 centimeters cubed, or 7.5 by 10 to the minus 4. Technically that's said per centimeter cubed. Usually we just multiply by 1,000 here, but to work out per centimeter cubed, which I don't like personally, you have to divide it by the 20 and write down your actual answer. So 0.0040375 moles per centimeter cubed. And then this, find the concentration of I2, so not our NaClO, not our sodium hypochlorite, and moles per litre. We've got how many moles per centimeter cubed, so just divide or multiply that by 1,000, sorry. I'll just write answer by 1,000. 0.0375 big M by 2, and then in grams per litre. To go from moles to grams, you multiply. When you're leaving moles, you always multiply, and by the relative molecular mass. So 0.0375 by the relative molecular mass of I2. Now iodine is 127, so I2 is 2 times 127 is 254. And you get 9.525. That's grams per litre. First one, lovely. Now, let's check that one, right? Where the hell are these answers now? I'll just presume it is. You just can let me know otherwise if it's not. But remember in that experiment anyway, why you use an excess of Ki, ensure the iodine stays in solution. That's what your forms your triiodide, your I3 minus. Now the next calculation I can see, question 2, 2K, a wee short one actually. 2K, so your organic experiment. A student steam distilled 18.6 grams of cloves and from the resulting isolation obtained 0.27 grams. Calculate the percentage yield. So remember, for the percentage yield, it's just simply actual over the theoretical, and to make anything a percent, multiply by 100. So in this question, what they actually got, he obtained 0.275 grams grams from how much of our cloves? 18.6 grams. Remember the lovely smell in this? Smell like Christmas. So 0.275, using our solvent extraction then. 18.6 and multiply it by 100. 1.478, 1.48% yield of our cloves. Solvent extraction. Right, where to next? We're going to another. So each of the 3 experiment questions had a calculation. Number 3, I kind of think water will come up this year, so make sure you know your free chlorine and things like that. So they'll probably be better than your free chlorine and your suspended solids, but my guesses wouldn't be great, but I imagine it's going to appear somewhere. It's been a while. So 3F, a 600 centimeter cube sample of water is found to contain 0.03 grams. So work with this first. 3 grams dissolved solids in 600 centimeters cubed. Now dissolved solids, remember, since they're dissolved, you can't remove them by filtration. They're removed by evaporation. I probably should work out the suspended solids first because you're moving by filtration, but well, whatever. That's what you normally do anyway. They want it in parts per million. Parts per million, remember, is the same as milligrams per litre. So 1 part per million is the same as 1 milligram per litre. So we'll change this here, English into maths. 0.036 grams. How do we say in? Maths, just a wee slash in 600. So 0.03 grams over 600. And if we get the number of grams in a litre, so multiply it by 1,000. You could have changed the grams to milligrams first. And you get 0.05 grams per litre. Now to change grams to milligrams, you multiply it by 1,000 and you get 50 milligrams per litre. And as we said there, milligrams per litre is the same as parts per million, since they did ask you for what is it in parts per million. The second thing, that was F part 1. F part 2 was the suspended solids, and in that question there was 0.84 grams suspended solids in 600. So again, we'll change the English into maths. How do we say in? 0.84 grams in 600 centimeters cubed. 0.84 grams in 600. We want to get to milligrams per litre, so we bring her up to 1,000. 0.84 and we get 1.4 grams per litre. Parts per million is the same as milligrams per litre. We have grams. To change grams into milligrams, you times it by 1,000 because it's used for very dilute solutions. So generally you'll be getting really small answers. That's 1,400 milligrams per litre, which is the same as 1,400 parts per million. I know we're racing through these. If there's any problems, just let me know. We'll go through it slowly. But yes, the next one, we're on to the short questions now. Question 4. And 4b actually looks difficult enough. Something that I never mentioned much to you in class, but you just could have footed it away and figured it out. So 4b, a 20 centimeters cube sample of 2 molar hydrochloric acid was diluted to 2 litres. So this is like the vinegar or the bleach. First thing I would probably work out with, there's different ways to do this, is how much it was diluted. So a 20 centimeters cube was diluted to 2 litres. 20 centimeters cubed to 2 litres. Now our units aren't the same there. And the way I would do that is 20 in 2 litres is 2,000. How much was it diluted? You can see there it's diluted 100 times. 1 over 100 is our dilution factor. just linking it into the vinegar and to the bleach. So if the original concentration of the undiluted was 2 molar, undiluted was 2 molar. My head's gone now, that sister ringing me. Undiluted was 2 molar. Now for the diluted is 100 times less concentrated. So 2 divided by 100 is 0.02 molar. Someone else might out, if you looked in the book, there's a formula there. I'll skip over to the other side here, just to show you another way. I know there is a formula in the book, so you know I kind of rarely use them. It's volume dilute by molarity dilute is equal to volume concentrated by molarity concentrated. So this is another way. It doesn't matter what order you put them in. So what do we have here? 20 centimeters is our concentrated. The molarity is 2. The volume diluted was 2 litres. You just have to make sure the units are the same. 2000, and we don't know its molarity. So 2000 m is equal to 40. M is equal to 40 over 2000. And it should give us the same as that other answer. 1 over 50 or 0.02 m. Which it is. So probably is more straightforward. But if you can figure it out using the big M and just taking your time with the dilution factor. 4E now. We'll not get all of these done. One hell of a video then. It's the electron configuration of copper. Now remember, copper and chromium are your two exceptions in this. So just take out your periodic table. We're just going along. So it's going to be 1s2, 2s2. Remember your S, the P blocks. 2s2 because you're in the second energy level. 2p6, 3s2, 3p6, 4s2. Now I'll say the wrong one first of all. 3d. Remember, it's like this block has just moved down one. 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. That's incorrect. This is one of your exceptions. So the wrong one here at the minute. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. This is all to do with stability. So a completely full sublevel has more stability associated with it. So one of your electrons moves from your 4s sublevel to your 3d, and then this is a half full sublevel, and this is a completely full sublevel. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. And there we can deduce as well your 3d energy is greater in energy than your 4s sublevel. Your 3d energy, 3d sublevel is greater in energy than your 4s sublevel. They asked you there for how many energy levels does that occupy? 4 energy levels. How many sublevels does it occupy? 1, 2, 3, 4, 5, 6, 7 sublevels. And then for your orbitals, remember you got to split them up into your x, y, z, them up, and then that's actually made up of 5. We just don't know what they are. But so we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, they never ask you for the 3D because we don't know how to split them up. Where are we now? I might do 4H. Nice wee one. 4H, right, the conjugate acid. Remember, for acid, we just have to think of added. So add on a proton, or H plus. That's all you've got to do. Conjugate acid, you add on a proton. So for the first one here, it's ammonia, right? The conjugate acid of ammonia, add on a proton. So how many hydrogens you got now? You've got 4, and you're adding on a plus charge. NH4 plus is the conjugate acid. if we add on an acid or add on a proton for an acid, you take it away for the base. So write the conjugate base, it says here, you take away a H plus, you take away a hydrogen, your NH2, your neutral here, you take away a positive charge, so it's like 0 minus a positive charge, your a minus is your conjugate base. 4a, oxidation numbers. Write the oxidation number of chromium and Cr2O3. Cr2O3. So oxygen's where you start, 3 times minus 2. Overall, this is neutral, there's no charge on it. So we're at minus 6. We want to get plus 6, so 2 times plus 3. So therefore, I would just be clear. Chromium's oxidation number is plus 3. And then your second one there is HCr O4 minus. Again, start with your oxygen, 4 times minus 2. Hydrogen's group 1, it's plus 1. Minus 8 plus 1 is minus 8 plus 1, minus 7. You want to get to minus 1. Minus 7 to minus 1, you add on 6. So therefore, Cr is plus 6. Remember, oxidation number is the charge that an atom, one atom, used to have. Where to now? Oh gee, hell a lot of them short questions, but easy marks. Find the percentage by mass of iron in Fe2O3. F. So work out the total relative molecular mass. 2 times 56. 3 times 16. What better way to spend a Saturday morning? 160. And now the total percentage of iron in it. So there's my total of iron. 112 over 160. To make anything a percent. Times it by 100. So 70%. If they ask you for the percentage of oxygen, it's simply 30%. If you wanted to check if you're right, you're not look at then 48 from your mass of your oxygen, and you get your 30%. It's the first 4 questions done. I'll go on to 5. Not much in 5. It'll be 5a part 3. Electronegativity values. Predict the type of bonding in phosphine, pH3. That was one of the, I remember the wee trick ones. It's pyramidal shape because it had 3 bond pairs, 1 lone pair. So you'd think it's polar, but it's non-polar because the electronegativity difference is very small. Really, hydrogen has a value of 2.2. Don't be trebling it up or anything. Or 2.20. Phosphine I think is 2.19. Take them two away, 0.01. Therefore, non-polar or pure covalent. They share them electrons equally. Potassium chloride, I must look up the values here. KCl. KCl, I have for K 0.82 and Cl 3.16. So KCl. Now, because there's something on the left and something on the right, a metal and a non-metal, I know it's going to be ionic. So I know it's going to be bigger than 1.8. 3.16 minus 0.82. Take them two away, and you get 2.34. Therefore, it's ionic. There's a complete separation of charge. Complete pull of electrons as greater than 1.8. The only other one, there 5CV. It's americium 241 used in your smoke detectors, and it undergoes alpha decay. Alpha particles are helium nuclei with a positive charge. So helium, there you go, the nucleus of a helium atom. Now 241 the left hand side must equal the right hand side. So 4 plus what gives you 2, 4, 1, 4 and 2, 3, 7. 2 and what gives you 95, 93. So you can see that now, 93 plus 2 gives you 95. And then you look up your periodic table, 93, isn't it MP? It is MP. Now generally I would put in plus energy, but they don't ask for it. So there's your two answers there. And I'll try and do one more. Number 6. Number 6. 6C. Fuels and heats of reaction. So here you have benzene C6H6 plus 7.5O2, 6CO2 plus 3H2O. The heats of formation are that calculate the heat of combustion. Alright, so the heat of combustion is equal to heat of formation. Suppose I may bring that over there. Heat of formation of products minus reactants. So heat of combustion or products. Carbon dioxide is a value of benzene 393.5. 6 by minus 393.5. The 6 just coming from this. Plus our water is minus 285.8. That just means the sum of the products. So keep them all in big dirty square brackets. Minus now here. And our reactants, we're only going to have one for benzene. Heat of formation is this, is just going to be 0. So benzene is plus 48.7. So there's 1 by 48.7. So these values are just given in the question. Now they do always expect these individual answers. 6 by minus 393.5 minus 2361. 3 by minus 285.8 minus 857.4 minus, and then that one, I can't even read it, 48.7. So that means our heat of combustion, and it is 1 mole. Remember, if there's a 2 there, divide this answer by 2. If there's a 3 there, divide this answer by 3. Heat of combustion, heat change in kilojoules when 1 mole, we're laughing. 1 mole is completely burned in excess oxygen. Minus 2361 minus 32. So it is kilojoules per mole. So no need to divide, but always think, go back to this. If there's a number in front of it, you have to divide this answer by that number. And since we see it's a minus, what do we know about this reaction? It's an exothermic reaction. Heat is given out. So heat's given out. Our energy of our products is less than the reactants. And remember, they asked you for activation energy all the way up. And there's our delta H, our minus thing there. 23 minutes. I might do question 7 as well. Equilibrium one. Sure, why not? So, equilibrium, fuel definitions at the start. We'll go straight into the calculation. We have PCl5 so we'll just layer out. So moles initially, change, and do this for all the types of equilibrium calculations. Moles at equilibrium, an equilibrium constant, or concentration, sorry, that just means moles per litre. That's what the square bracket's all about. They will have asked you actually in part 2, write the Kc for this. So Kc, it's products over your reactants. So there's my products. PCl3, Cl2 over PCl5. And remember, if there's a number in front of it, there was a 2 in front of this, that's becomes squared. And if there's charges on them, Put in them fucking charges, because you're mad for leaving them out. So when 20.85 grams of phosphorus pentachloride, there's my moles initially. So 20.85, I know this mass now because I've seen this one before. It's 208.5. Work out the relative molecular mass of that, and you'll get that. And you fire out in your calculator, you get 0.1 moles initially. These are 0 and 0. So this 208.5 just comes from the mass of this 5 by 35.5, and phosphorus is 31 by 31. Now, 5 litre container, that's going to come in down here. Temperature 500 because equilibrium constants are temperature dependent. And it was found that at equilibrium, there's my at equilibrium, 75% dissociated. Now you can either say that there's 25% remaining here, or you can work out 75%. That's how much dissociated. That's actually the change. Or if you like, 0.1 minus that, we'll go in reverse ways. Moles at equilibrium because 75 dissociated, there's 25% remaining. Now what you could do, now I seen the answer there, work out the difference in these. 0.1 minus that, there's my change. Now what's going to happen to my concentration of my reactants? They're going to decrease. So it's a minus, and then the ratio in which these react is 1 is to 1 is to 1. So if this goes down, minus 0.075, this is going to go up. So in the mocks before, you forgot to double them or treble them because the numbers in front of them. I think I was looking at the Haber process. So it's not always just the same. And then the equilibrium concentration, it says 5 litres. So that wants it in moles per litre. Zero 0.015, 0.005. There's all my values. This is working out the value of Kc. The other type of calculation is when they've given you the value of Kc and then throw it up into that. Therefore Kc is your products over your reactants. So I'm just putting these values in moles per litre. That's what them square brackets means in there. You throw that in the calculator. (9 over 200), which will give you a nice decimal as well, 0.045. So equilibrium very much on the left hand side. I'll just do the other wee bits of theory. It says when the temperature mixture is increased, the PCl5 further decomposes. So when you increase the temperature, you favour the endothermic reaction. Increased temperature, endothermic. So is the reaction endothermic? It is, because it's pushing this one forward. It is endothermic. As you increase the temperature, you favour the endothermic reaction. And for V, state the effect in the yield of PCl5, which is this, if more Cl2 is added. So if we increase the concentration of Cl2, the system responds in such a way as to decrease the concentration of Cl2. Equilibrium shifts to the left, forming more PCl5. So the concentration of PCl5 increases for the first scenario. This is all using Le Chatelier. And for part 2, the pressure is increased. So are they all gases? They are, because they've all got the G's here. There's an unequal number on either side. We're laughing. Pressure does have an effect. So if we increase the pressure, we favour the side of the smaller number of molecules. Here we have 1 molecule on the left, 2 on the right. So favour the side with the smaller number of molecules and pushing equilibrium to the left hand side and forming more PCl5. So in both cases, PCl5 increased. I'll stop it here and then I'll do another video from 8. Well, 8, 9 don't actually need any. 10, 11.